Now again, with the multivariate Gaussian distribution, we can look at the conditional distribution. This is a little bit tedious to derive. I'm not going to do it, and it also requires a little bit insight in terms of linear algebra and some random variable manipulations. So I'm not. I'm just going to leave it out. I'll just give the result here. For the derivation, you can just check this resource out. Um, let's say you have a multivariate Gaussian distribution of size n, let's say, it doesn't really matter. We know the mean vector and we know the covariance matrix. And let's say we partition this into two parts, x sub a and x sub b. Okay. And of course, the dimension of x will be equal to the sum of these dimensions. And also the mean vector here and the covariance matrix are partitioned accordingly. Okay, so this equals the size of the dimension of A, dimension of B here. Again, this here, dimension of A, dimension of B, dimension of A, dimension of B, let's say. Okay, and in this case, it's possible to derive the conditional distribution of x sub A given x sub B. It's also Gaussian. It's also multivariate jointly Gaussian. And this is the mean vector now. And this is the covariance matrix of this conditional distribution. Okay. You can also derive this using characteristic functions. Again, I'm not going to do it because it's a little bit tedious. It takes time. But the point here is, if you have a joint Gaussian distribution, any subset will be again jointly Gaussian, and any conditional distribution among the components will also be Gaussian. Okay, so that's the beauty of Gaussian distribution. Okay, as I said, two marginally Gaussians are not necessarily jointly Gaussian. This is very important, okay? I cannot emphasize this enough. This is a very frequently mistaked issue, okay? Here's a classical example. You can see this in all sorts of resources, also probably in Wikipedia, I guess, also in our book. Let's say a random variable x is standard Gaussian, and you have a fair coin. It's tossed independent of x, so we have a Bernoulli distribution, so to speak. And we define a new random variable y by taking x if the coin outcome is heads, and taking minus x if the outcome is tail. Now you see, since x is standard Gaussian, minus x is also standard Gaussian. Okay, then when you write the marginal distribution of y, if you derive the PDF of y, well, we didn't see functions of random variables, so at this point maybe you can't do it, but it's not that difficult. If you do it, you'll see that it's also standard Gaussian. Okay. However, if you look at the joint distribution, you'll see that it's not bivariate Gaussian. In fact, there is a plot of this function on Casebook. I recommend all of you check it out. And this is a very important point. Marginal Gaussian doesn't necessarily mean it will be jointly Gaussian also. The other side is true. If you have jointly Gaussians, the marginals or any collection will be still jointly Gaussian. Okay, so finally we will talk about uncorrelated joint Gaussians. Let's say you have a set of joint Gaussian random variables, x1 through xn, and we will assume here all pairs are uncorrelated. And we will see what happens here. Now here, since we say all pairs are uncorrelated, that means all covariances are zero. Therefore, the covariance matrix is diagonal. And on the diagonals, you see the variances. And when you have a diagonal matrix, it's very easy to invert it, and it's very easy to obtain its determinant. The determinant is clearly the product of all these, and the inverse is obtained by just taking the reciprocal of these values on the diagonal. So if you write this expression, it's quite easy to write because this is a diagonal matrix. And if you actually expand it, you get this. The sum of these terms, xi minus mu sub xi squared divided by variance of xi. Now, you see, this appears here in the expected value. Therefore, we can write the joint PDF of these jointly Gaussian random variables as this expression e to the power this, e to the power minus 1/2 times this, divided by 2 to the power n over 2 times the square root of the determinant of this matrix, covariance matrix. And if you arrange this, you see a summation in the exponent means a product of exponential functions. So I can write them each individually, and I can also separate these to obtain this. And what is this? This is nothing but a marginal Gaussian PDF. So at the end, I see that the joint PDF of the uncorrelated joint Gaussians is equal to the product of marginal Gaussians. What does this mean? That means uncorrelated joint Gaussians are also independent. This is also a very important property of Gaussian distribution. Remember, in general, I have emphasized that uncorrelatedness does not imply independence. Independence implies uncorrelatedness, but it's not the other way around. But only for Gaussian distributions, uncorrelatedness also implies independence. Now, in the case of not jointly Gaussians, but general Gaussians, let's say, well, uncorrelated joint Gaussians are also dependent, but two uncorrelated Gaussians may not be independent. Why? Because they may not be jointly Gaussian. If you remember the example earlier, okay, here I said that X is standard Gaussian, Y turns out also to be standard Gaussian, but they are not independent and they are not jointly Gaussian. And in this case, they turn out to be uncorrelated. If you compute the correlation, it turns out to be 0, the correlation coefficient, but they are not clearly independent because one of them is defined in terms of the other. Therefore, this illustrates that when you don't have a joint relationship, if they are not jointly Gaussian, even if they are marginally Gaussian, they may not be independent even if they are uncorrelated, okay? So being joint Gaussian is very important also in that sense.